Yes.
Okay. Let's just talk about tangent a half theta over 2 for a moment.
Okay.
Sine of theta over 2 is plus or minus 1 minus cosine theta over 2. And cosine theta over 2 is plus or minus 1 plus cosine theta over 2. And therefore, the tangent that I find, I looked it up and I noticed there's 3 separate identities for tangent of theta over 2.
Yeah.
And the one that's really the easiest, if you know the sine and the cosine, well, and if you know that tangent is sine over cosine, then it's this one right here. You see how I get that?
Yeah.
So
Okay.
to me, you don't actually have to memorize tangent. If you've memorized sine and cosine, you can figure this one out. Now, I did notice that my book did list the one that you had talked about, which is this one. And that might actually look simpler, but believe it or not, it's harder because I've got to know what both cosine and sine are to do this one.
Right.
Whereas to do this one, is all I got to know is cosine. Now, it's not totally true that all I have to know is cosine. I have to know which quadrant it's in so that I can choose the proper plus or minus. So it perhaps is about the same degree of difficulty as this one. Notice that this one does not have a plus or minus. In other words, the plus or minus is going to take care of itself
Okay.
in the bottom one. And then, of course, there's the third one, which is a common trig identity, which is sine of theta over 1 plus cosine of theta. In other words, you are frequently asked to verify that. That's one of the most favorite verifying identity problems that there is. So that's why when we talked about it, I was puzzled that you weren't starting it out with square root of, because I don't believe I ever used that one, the second one. I've always used this one here. Now, they're identities, so they're going to give you the same answer, but this one here is actually probably a little easier to memorize if you've memorized sine and cosine. Notice, it's just this numerator divided by this denominator. All right.
Okay.
What else do you have that you want to go over tonight?
So if cosecant of theta equals -5/2 and theta is in between pi and 3 pi over 2.
I will call you. There's the static.
Okay.
It happens at the 4-minute mark.
Yes.
It was perfect until then. Let me call you. Go ahead and take yours off of computer. I have to leave mine on computer audio so that the recording still records the audio.
Okay.
You there?
Yeah, hi.
Okay. Yeah, hi.
Okay, so
Turn my volume up a little bit. Okay.
with that, find sine of theta over 2.
All right. If the cosecant of theta is minus 5 over 2, what's the sine of theta?
Negative 2/5.
Now, since the sine of theta over 2 is defined in terms of cosine, right?
Right.
So we got to figure out what the cosine of theta is. Well, if I know what the sine of theta is, and I know what quadrant it's in, and I do, it's theta's in the third, how do I figure out the cosine of theta?
Well, you have to draw a triangle.
And label theta.
And sine opposite is 2. And the hypotenuse is 5. Which makes the adjacent side root 21.
Okay. So what's the cosine of theta?
Root 21 over 5.
All right. Now that we know the cosine of theta, and it's the third quadrant, so what is the sign, the plus or minus sign on the cosine of theta?
Negative.
Okay. Now let's apply our formula. It's plus or minus the square root of 1 minus cosine of theta all over 2. So that's straightforward enough. Are we going to choose the plus or the minus sign?
The minus sign.
Well, this gets a little bit deeper. If theta is in the third quadrant, where is theta over 2?
The first quadrant?
Second, actually. Think of any angle between 180 and 270, divide it in half, and you get something between 90 and 135. Right?
Okay, right.
So that puts it in the second quadrant, theta over 2, and sine is positive in the second quadrant. So I'm going to choose the plus side of that. So it's plus the square root. What's the rest of it?
1 minus root.
It's negative root 21 over 5. Now this can get a little confusing because theta is in the third quadrant, but theta over 2 is in the second quadrant. And that's why you have to choose the plus, because we're talking about theta over 2, right? If we know theta is in the third, then we know theta over 2 is in the second. Just like if you knew theta was in the second, you would know theta over 2 had to be in the first. So you have to figure out two things here. You have to figure out what quadrant theta is in, and you have to figure out what quadrant theta over 2 is in.
Okay.
Now, if theta is in the fourth, then that means it's between 270 and 360. So theta over 2 would be between 135 and 180. So if theta was in the fourth, theta over 2 would still be in the second.
Okay.
And that's the way you do it. Turn it into degrees and then divide it in half and figure out where it lies.
Right.
Now, I can do a little bit to simplify this answer. Not a lot. It's 5 plus root 21 over 10. In other words, if I simplify this, it becomes plus the square root. Let's see, the 1 becomes 5 over 5, so I got 5 plus root 21 over 5 over 2. So there's my answer for sine of theta over 2. Again, notice the radical inside the radical. It's always kind of amazed me how that can be the same as some other number.
Yeah.
We talked about that last night, where if you're doing tangent, I think, where you had multiple identities, and one of them gave you a radical under a radical, and the other one, and it wasn't tangent, it was the sine of 195 degrees, and we had two different ways to do it. We could use the double angle formula, or we could use the sum and difference formula. And they both gave very different looking answers, but they were the same number.
Right.
All right, what else do you got?
So using the same cosecant and same quadrant for theta, find cosine of 2 theta.
Hold on, let me see if I can get back to that page. Wow. For some reason, this program has completely changed. I don't know how to get back to my last page. All right. Let me just start with a new page again. I'm sorry. What was it again? Cosecant is equal to minus 5 over 2, and we're in third quadrant for theta.
Yes.
And what was the question?
Cosine of 2 theta.
Okay. Let's talk about the identity for this, because this also has 3 different identities. And you might wonder, well, how come it does? And there's a reason, a pretty good reason. Let me first of all list them all. And notice kind of the similarities. In other words, first of all, that's strange. It's not cosine plus sine, which would be equal to 1, right?
Right.
So it's fairly easy to remember cosine squared minus sine squared. The second one is completely in terms of cosine. There's no sine involved. So that can be valuable at times. If I have a trig equation where I've got a cosine of theta and a cosine of 2 theta, well, I can turn the cosine of 2 theta into nothing but cosines, and then I got a trig equation with just cosine only, and I can solve it. So there's times where you'd want to use the second one. And then there's times where you'd want to use the third one. In other words, the third one, the only thing you have to know is sine squared of theta. You don't have to know cosine.
Right.
Which one should we use here?
The 2 cosine squared.
Well, that means I got to figure out cosine.
Oh, yeah, no, the sine.
Yeah, in other words, I can figure out sine pretty easily.
Right.
Sine is that. So if sine is all I know, then I'm going to use this one. Piece of cake if I use that one.
Yeah.
So that's why they give you 3 identities, is because depending on the nature of the problem, you might want to use one over the other. So I want 1 minus 2 times minus 2/5 squared. And notice, I don't even have to worry about the quadrant because minus 2/5 squared is a positive number.
Right.
So it doesn't matter what quadrant we're in. I don't think. Hold on a second. It might. Well, no, this is absolute. There's no plus or minus sign in front of this. So this should give us the correct answer. What is that? 1 minus 2 times 4/25. So we have 1 minus 8/25. So that's 17/25. So that's what the cosine of 2 theta is, where theta is in the third quadrant. Third quadrant means from 180 to 270. Well, if we multiply that by 2, we're going to be from 360 to 540. That could be first or second quadrant. We don't know.
Okay.
But the answer tells us it's first quadrant. In other words, if I had gotten a negative answer, it would have been okay because 360 to 540, first of all, do you understand that's the same as 0 to 180?
Yes.
So it could be first or second quadrant. If we know theta's in the third, then 2 theta has to be either the first or the second. And we don't have to know which it is. Because all we have to do is use the proper formula. And in fact, I could probably use either of these formulas. As long as I know that theta is in the third, I could use this because I could figure out what cosine of theta is by drawing the triangle, labeling 2, 5, root 21. So I could go through the same analysis and figure out that the cosine of theta is root 21 over 5. And then I could use this formula if I wanted. Or this formula, because now I know cosine and sine. But if I use this third formula, I don't have to figure out cosine.
Right.
Also notice the similarities in these. In other words, this might look hard to memorize because there's 3 of them. But not really. There's a lot of similar stuff going on here. In other words, first of all 3 of them have subtraction, no addition, right? This one is, there's a 2 in front of the trig function that's being squared in the bottom 2. In other words, it's 2 cosine squared minus 1, or it's 1 minus 2 sine squared. There's a similarity between those 2 that make it easier to memorize. And you know the top one, it can't be cosine squared plus sine squared because that's the number 1. And we know subtraction's going on, so the first one is fairly easy to memorize also.
Yeah.
All right, what else? One thing I forgot to mention yesterday. Let's talk about it again here. I'll leave that up in case you have another problem involving the cosecant. But you had one yesterday that was 9 pi over 8, right?
Yes.
And
tangent of 9 pi over 8.
yeah, and we wanted to know what that was. Well, that's not a common one, because pi over 8 is not a common one.
Right.
So I did two things that perhaps you weren't aware I was doing. One, I divided it by 2 to see whether that would be a common angle, and it was not, because 9 pi over 16 is also not common. And you know what I mean by common, it's not on the unit circle.
Yes.
Or I multiplied it by 2, which gave me 18 pi over 8, and that is a common angle. That is pi over 4. So whenever you see an uncommon angle that they're asking for a specific value, you can always tell by either having it or doubling it. If either of those produces a common angle, then you know what to do. In other words, if doubling it produces the common angle, then I've got to do sine of theta over 2. I got to do the opposite.
Okay.
If having it produces the common angle, then I got to do tangent of 2 theta. But the first thing you do is have it and double it to see if either of those makes one of your unit circle angles, and if it does, then you can use the half or double angle to figure it out.
Okay.
And even this problem, in other words, we used the second identity, right?
Right.
And we would have been better off using the original, because the original only requires you to know the cosine. That's all the original requires is cosine. Whereas you and I had to know sine. In other words, we had to know cosine and sine, because what we used was 1 minus cosine of theta all over sine of theta. So we had to figure out both the cosine of theta and the sine of theta. If we use that one, we only have to figure out cosine of theta, but we have to know what quadrant it's in also to figure out whether to choose the plus or the minus.
Okay.
So whenever you have these unusual angles, and in other words, there's 3 ways to handle unusual angles. You got sum and difference, you got double angle, or you got half angle.
Right.
Well, if you know that you're supposed to use either half or double, then the first thing you should do is take half of it or double it and see if you get a unit circle angle. If you know that you can use sum and difference, it's a whole different story. In other words, I can probably split 9 pi over 8 up into a number of sums and differences, and that's a bit tricky sometimes. In other words, you have to practice that a little bit to figure out how to split 9 pi over 8 up into 2 angles that you know. Right off my head, I can't think of how to do it. Maybe it's not that doable with 9 pi over 8. Sometimes it was like 195 degrees. It took me a while to figure out that that was 225 minus 30, and both of these are knowable without a calculator.
Right.
But it's also, if I can see that taking half of that doesn't do any good, but if I double it, I get 390, and that is a common angle. That's 30. So I could solve the 195 degree angle by 2 different methods. I could do it by sum and difference, or I could do it by the half angle. Not the double angle, the half angle. Notice that if I can double the angle and get a unit circle angle, then I want to use the half angle formula. If I can take half of it and get a unit circle angle, then I want to use the double angle formula.
Right.
You're always doing the opposite of what you can manufacture with the thing. All right, what else you got?
More verifying verifying identities.
Okay.
It's sine of theta times cotangent of theta plus tangent of theta, all in the parentheses, equals secant of theta.
What do you think we should do here as a first step?
Write all of the functions as sine and cosine.
Yeah, and including knowing that the right side is the same as 1 over cosine. I don't have to do that, but it's nice to know that that's really what I'm going to try to turn the left side into. Okay, in other words, some teachers might even tell you you cannot mess with the right side. You can only mess with the left. That's fine, as long as I know that the last step on the left has to be this.
Okay.
Okay, so since there's one sine in here and there's no good way to turn those into anything else, then let's turn them into sines and cosines. So that is cosine over sine plus sine over cosine. Now, let me think for a second. If I distribute that, I get cosine plus sine squared over cosine. Now add those two together. What's the common denominator? In other words, we're adding those two together. Common denominator is?
Cosine.
Okay. What goes on the top left?
Cosine squared plus sine squared. Right.
What's cosine squared plus sine squared equal to?
1.
1 over cosine.
Yeah. Okay.
Okay. So I guess almost a general rule of thumb, maybe not always, but if you see a sine or a cosine in the thing, then that's probably the way to go, is to turn everything else into sines and cosines.
Right.
Unless I was looking at tangent squared plus 1, you know, if that was what I was looking at, then I would certainly turn that first into secant squared. In other words, always do the obvious things first. But there's nothing obvious to be done in this particular problem other than turn everything into sines and cosines. Okay, what else?
Cosine of theta over 1 plus sine plus 1 plus sine over cosine equals 2 times secant of theta.
Well, I think I'd be inclined to just add those two fractions, knowing that what I'm trying to produce is actually this, right?
Right.
Okay, which has cosine in it. So if I just do the algebra, I should end up with 2 over cosine theta. So help me do the algebra.
So
Common denominator.
cosine squared.
Don't distribute it. Oh, I see what you're doing. Okay, sorry. Over what?
Over cosine plus cosine times sine.
Don't distribute it. That's what I meant.
Don't distribute.
Don't distribute it, ever.
Okay.
You can see why?
Yeah, okay. Right.
First of all, by not distributing it, I can tell whether I've made a mistake going from this step to this step. And
Okay.
I can see that I have not. In other words, I can cancel out that cosine with one of those exponents and I end up with what I started with. That's the key reason you don't distribute the denominator. You leave it in factored format. Is because you're going to probably be able to cancel stuff. And if you were to distribute it, it would be harder to see what you might be able to cancel.
Right.
And what goes over here? In the numerator?
1 plus sine.
Squared.
Oh, okay. Right. Don't say.
And I figure it out in my head. I figure it out by making sure that I put whatever I have to put there so that it's equal to that. That's how I do it. That's technically, there's better ways to put it, but that's how I do it. Okay. Now, we're going to have to, well, let's see. Now, hold on a second. So I have a common denominator, right?
Right.
So I can do this. What's the top turn into? Oh, no, hold on a second. I can also cancel that exponent with that cosine of theta.
Okay. Right.
Hold on, I'm thinking. This is not coming out to what I want it to come out to be. Hold on. Let me go back. I feel like I made a mistake. Let's see. That was cosine squared over 1 plus sine theta times cosine theta. And whenever it goes awry, I try to go back to where I know is correct. Now that's correct, is it not, for the left side? I haven't changed it?
No.
Okay. Now let's distribute. Well, now let's do this. So the top becomes cosine squared plus 1 plus sine theta quantity squared all over 1 plus sine theta. Yeah, now I can see where I made my algebra mistake. I can't cancel anything.
Oh, right. Okay.
Okay. What I can do is expand the top. How does the top expand? What's 1 plus sine theta quantity squared?
1 plus 2 sine plus sine squared.
Okay, still all over this. Now I've got a cosine squared there, a sine squared there. I know that's 1.
Yeah.
I got another 1, so I got 2. So here, let me scroll down a little bit here. So here's my new numerator. 2 plus 2 sine theta all over 1 plus sine theta times cosine theta. I think this is going to convince you that you never want to distribute the bottom, because otherwise we wouldn't see this answer. Now I can factor out a 2 from the numerator, and I have 1 plus sine theta left over. Now in the denominator, I got 1 plus sine theta times cosine theta. I can cancel that with that, and I end up with my 2 over cosine theta, which is 2 secant theta.
Oh, wow.
But notice, had I multiplied out the bottom, I would have liable to never seen that I could cancel out that 1 plus sine theta with this 1 plus sine theta.
Right.
But I did have to expand that. In other words, sometimes you do have to multiply it out. Sometimes you're better off not. I guess I would say usually when you have to multiply stuff out, it's in the numerator, and usually you don't want to multiply it out when it's in the denominator. I don't know how else to put it. That's the only guidelines I can recall, is that I'm never multiplying it out in the denominator, and sometimes I am in the numerator.
Okay.
All right. What else? That's a good one. I've heard that one before. I've done that one before.
Yeah, that was...
Yeah, that's a very clever one because it requires so much. You have to add 2 very complex fractions, and then you have to do a lot of tricky stuff before you can make it look like 2 over cosine theta.
Yeah. Well, I don't have any more problems.
Okay. Well, if you're good to go, we can be done with it. When's your test? Tomorrow?
Yeah, tomorrow morning.
Okay. There's no different types. We've done double angle, we've done half angle, we've done verifying identities. Have we solved equations? Or do you have to do that?
I don't think we have to. It's not on my review, and I don't...
Okay. So if you had something like this, you wouldn't have to do that.
No.
Okay. We won't go there then. I don't want to confuse you with additional information. You're probably going to do that next.
Yeah.
Solving trig equations. And I will say this, that you'll never run into verifying trig equations in the real world. That's strictly an exercise helping you. And by now, you probably believe me when I told you that the reason for that is to teach you your identities. I guarantee you know your identities better now than you used to.
Yeah.
Yeah, because you got to know them. You got to know them so good to be able to verify trig identities.
Right. Know all the different properties.
However, trig equations you do run into in the real world frequently. There's all kinds of real world trig equations that have to be solved. And frequently the way to solve them is by using your common trig identities.
Right.
So it's not that you don't ever have to use trig identities in the real world. It's just that there's no real world problems that says make sure this is the same as this.
Right. It's a part of the trig equation.
Yeah, just for example, let's say I did have cosine of 2 theta minus cosine of theta plus 1 equals 0. Okay? Well, you can't solve this as long as that's 2 theta and that's theta. You got to get it usually into the same trig function, and I'm going to use the trig identity here that is 2 cosine squared theta minus 1. Notice why I'm going to use that.
Right.
Because now I've got it in a quadratic. Everything's in cosine of theta. This term's squared, this term is not, and I got a constant. So I can apply the quadratic formula if I can't factor it. But if I can factor it, then I will have 2 different answers and be able to solve for theta. So this would have been a little bit better probably if I'd have made this number 2 instead of 1. But you can see that I could come up with a quadratic. In other words, just get you a little bit ahead here. Let me think for a second. Can you factor that? Notice that it is a quadratic. It's what I call a quadratic in disguise, because the solution is cosine theta plus 1 times cosine theta minus 2.
Okay.
Notice that produces the perfect first term, middle term, and number. And now that I know this times this is equal to 0, well, now that I can say cosine theta equals minus 1 or cosine theta equals 2, and since cosine theta can never be equal to 2, I throw out that solution as extraneous, and there's only one place in the unit circle where cosine theta equals minus 1, and that's theta equals pi, or 180 degrees.
Right.
So that's the solution to that equation. It's only true when theta is equal to pi or multiples of 2 pi. In other words, pi, 3 pi, 5 pi, and so forth.
Okay.
Well, I'd say you're good to go. If you don't have any more questions.
Yeah, I think so.
Okay.
Thank you very much, Mr. Collins.
You're welcome. I will talk to you next time, and tonight I'll just charge for 3/4 of an hour.
Oh, okay. Thank you very much.
Yeah, no, I always do that. If it goes less than an hour, I don't charge it for a full hour.
Thank you.
All right, William. I will talk.
Good night.
Good luck on your test tomorrow, and I'll talk to you next time.